Alright, so fine. Till this point, we have already completed with electric field, Gauss's law, electric flux, and the quick review session of all these articles. And I personally feel that you must have gone through all this, you must be aware of all this, and now it is the right time to start with the numericals. You know, the numerical segment of this section is very catchy. The numerical section of this segment is really very interesting, and it needs a defined effort also. With the effort I mean that you have to be very consistent with the videos, very consistent with the numericals that we are discussing, and very important to understand, these numericals are not just the singleton numericals. What I mean to say is with these lines, that say if I am doing one numerical, that numerical actually is a concept. Numerical itself is a concept. Based on that numerical, you will be in a position to sort out many such numericals in the due course of time. So what I personally suggest you is, don't leave any single video. Go through every video very clearly. Second point, these numericals, whichsoever I am going to teach in during these lectures, all these numericals are a composite numerical. What I mean to say with this is that every numerical that I am going to teach is a baseline for many such numericals which are yet going to come in the due course of other competition exams. So please be very focused, be very clear about all these numericals, and I'm telling you, you will not find anywhere lagging the moment you are going to do these numericals very effectively. So let's move on to the concepts like straight conductor, the ring, and the disc. First of all, we are going to take all these three segments once again, and the numericals based on these three segments we are going to discuss, of course, but let me again once write in the quicker session about this straight wire having linear charge density lambda, and it can be of infinite length, it can be of a defined length, whatsoever. So you very well know it is lambda by 4 pi epsilon naught a, then sine phi 1 plus sine phi 2, and this is the Ex value, and Ei value was lambda by 4 pi epsilon naught a cos phi 1 minus cos phi 2. Hope you remember this. That is Ex and Ey for a defined length of wire with the limits, like say this point is P, this distance is A, and this limit was phi 1 and this limit was considered to be phi 2, right? And the similar segment that we have done in the further succession was, we have taken phi 1 and phi 2 to be 90 degrees, and we have got the value of Ex, and correspondingly Ey came out to be 0. This is all that we have done. Similarly, for a ring at a point P at a distance x and the radius of the ring be r, we have got the value E at this point, which is obviously Ex, because the rest of the things have balanced out Ey. There was no component like Ey here. And what is the value of Ex? Ex came out to be k, or I can write it like 1 by 4 pi epsilon naught qx upon x square plus r square raised to the power 3 by 2, or r square plus x square raised to the power 3 by 2. Right? And again, linear charge density is lambda, or the total charge on the ring is q. And in this case, we are considering the charge density to be sigma. So Ex is given by sigma by 2 epsilon naught 1 minus x divided by under root of x square plus r square. This is again that we have done. The sigma by 2 epsilon naught 1 minus x upon under root of x square plus r square. In the same case, Ey will be vanished because it is going to balance out. And these all three segments are important because these three segments, even I have told you in the previous videos that these three segments are going to be compositely used in the numericals. That I am going to teach you by this time, right? Now, little tidbits of this and this section, because this is already prominently clear with us, because this is one condition, phi1 and phi2 can be taken 90 degree and we are going to get the value of Ex, and correspondingly we are going to get the value of Ey. Now I am going to talk about specifically Ex, a kind of question that is very common in this section. Like, the question is, at what point on the axis the electric field is maximum? Right? So, hope you have got the statement that at what point or which point on the axis, this is the axis, the electric field is maximum. Right? So this is what we have to find out. So in this case that we have to find out the value of electric field to be maximum, we are going to use the very simple logic of the derivatives. We are going to find out the derivative and we are going to put this derivative to be equal to 0, and correspondingly you will get the value of the point where the value is maximum that you are going to get, and in fact putting that value of x over here you will get the maximum value of Ex, means Ex max even you can get, right? This is not very difficult, but yes, you must keep this in your mind, and if somebody doesn't know this, no problem, I'm just going to work it out quickly. So ddx of 1 by 4 pi epsilon naught qx by x square plus r square raised to power 3 by 2. Now it is 1 by 4 pi epsilon naught, given q is constant, so I'm going to work out ddx of x by x square plus r square raised to power 3 by 2. And now in the quicker succession you must be knowing how to sort it out, because it is the simple division rule in the derivative, where we are going to do square of the derivative, square of the denominator, I'm sorry, this is square of the denominator derivative of numerator, that is 1, plus numerator derivative of denominator, that is 3 by 2 x square plus r square raised to power 1 by 2 into 2x, right? So now you can, it's minus, it's minus, what I'm doing, it's minus, it's x square हो गया, 2 we are going to cancelize with 2, so it is x square plus r square raised to power 3 by 2 minus 3x square plus r square raised to power 1 by 2 divided by x square plus r square whole cube into q by 4 by epsilon naught, which is there itself. I'm just going to simplify this little more, means this I have already cancelled. 3x square plus r square raised to power 1 by 2, x square plus r square raised to power 3 by 2, and x square plus r square q by 4 by epsilon naught in this position. So I can write it somewhere here. So let me write it. It is somewhat like this: x square plus r square raised to power 3 by 2 minus x square plus r square raised to power 1 by 2 and 3x square along with this divided by x square plus r square whole cube, right? Further you wish to solve it, you can further solve it, but more than sufficient. You have got this value of dEx by dx. Now you just have to put it to be 0. The moment you're going to put it 0, so obviously it will come out to be x square plus r square raised to power 3 by 2 minus x square plus r square raised to power 1 by 2 into 3x square equals to 0 because the denominator will move to this side. It will vanish, this is going to move on this side, it is going to vanish, and ultimately it is x square plus r square raised to power 3 by 2 is equal to x square plus r square raised to power 1 by 2 into 3x square. And now you can take it down, 3 by 2 minus 1 by 2, it will come out to be 1. So it is x square plus r square, which is equal to 3x square. You can take 3x square here, it is r square is equal to 2x square. So it implies x square is equal to r by 2 right. So this is the value of x because I have adjusted the square directly here. Okay, simple. Done. So x is equal to r by root 2 is that location. Suppose this is r and say I am considering this to be r divided by root 2 and so this point is p prime, and p prime is the point where the electric field is supposed to be maximum. Right, maybe onto the left or maybe onto the right, maybe onto the left. So it is 0 at this point, maximum at this point, and equilaterally or symmetrically if we move, it is going to be maximum on the other side also. So that is a clear notion of this, and you know this is the not very higher order segment, but yes important. Because based on these lines, many other numericals can be asked. We have to be really very focused and clear. We have to do it in the very consistent way. Let's go with the derivative. Let's put it to be equal. We are going to put this derivative to be equal to 0, which is the condition for getting the maxima. We are going to sort out. We have got the value of x to be r by root 2, and perpetually we have got the result. And one more thing I am going to do right here now, if you might have gone through it and you are clear with it, let me give me a little more to represent here one more particular thing. I just have wiped it off. If I am going to draw this electric field graphically, I must say the electric field is 0 at this point, and electric field is going to be maximum at this point and maximum on this side, right? So we are going to represent, the only difference is the direction of the field. So how I am going to draw, see, right? So after this point it is again going to reduce, and this curve is going to be infinite, means it's not going to touch this axis, and this is the maxima, and if you must have studied the asymptotes, the curvatures and all that, which we normally teach the students in the quicker session for the advanced, so you must be knowing why it has come parallel. But anyways, right at this point of time I am not going more deeper into it, so it's sufficient. So at this particular point or the location, this is origin and this is r by root 2, this is again r by root 2, but over here the electric field is maximum on one side and maximum on the another side, means the direction only will be reversed, right? That is the point. That is the point that we have discussed in that, right? So again, repeatedly I am saying this, that it's not very difficult, but yes, very important to understand, very important to consider it as far as the numericals are concerned. Okay, so see, one segment ring is covered, equilaterally there is another segment disk, and what normally is going to cover in what normally is going to be asked in the disk, that is I am going to explain right now. Let me just wipe it off. In case of disk, you know, we very well know that this is the expression, right? Ex is equal to sigma by, let me write it again, 2 epsilon naught 1 minus x by under root of r square plus x square or x square plus r, the way you wish to write. This is the value of Ex, sigma by 2 epsilon naught 1 minus x by under root of x square plus r square plus x square under root. Right. Now the question comes like this. What if the disk becomes very large? Means infinite disk. Means r is much greater than x. Right. What we are going to do? Clear? R, I have just taken common from this square root, right? And now r came out 1 plus x square by r square, and now r is much larger than x. It means this section is now negligible. I can just remove this section from the square root because r is quite larger. So when we are going to put it in denominator, the complete factor can be avoided. So now what is going to and still r is larger than x. So even this segment, which is again going to be subtracted from 1, is a very small segment. So approximately I can replace it by sigma by 2 epsilon naught. As simple as that. So it means for an infinite sheet, I can consider Ex to be just sigma by 2 epsilon naught, and this complete factor is a redundant factor. Right? We can just remove this factor. Why? Because the x is r is pretty larger than the value of x. So this factor once I just wiped off, and another way again, since r is quite larger, so just for a small approximation I can even remove this value because r is approaching to infinity. If r is approaching to infinity, x by infinity is 0. So sigma by 2 epsilon naught into 1, it is sigma by 2 epsilon naught. As simple as that. So let me relate this, because now you have done Gauss's law. Let me relate it with this square sheet. You might have remembered, and there was a point P, and what was the electric field near the infinite plane sheet of charge having surface charge density sigma? You must have you have done it like sigma by 2 epsilon naught. So this is again very clear that we have done it earlier through Gauss's law, and we are equivalently doing it in this particular segment because this is a small disk. For the small disk, for a defined radius, this expression is viable. But for a very large disk, for an infinite value of the disk, infinite value of the radius, in that case, we are going to remove this complete segment and we are going to make it negligible, and just we are left with sigma by 2 epsilon naught. As simple as that. This is again very important for you to understand. In case the word infinite comes in, then you have to consider all these things right into the consideration. Okay, so see quickly just 1, 2 and 3, and we have worked out a bit of the sections in this particular articles.